Though I mentioned that the previous video was the last, well, after that time, I thought I could make two bonus videos. So, so I'll make these two videos and I'll close the playlist finally. And in this first one, I'll be looking at Gaussian processes. Gaussian processes. Now, Gauss is that mathematician who seemed to have an input in every aspect of mathematics, right? So talking about Gaussian processes, first of all, we look at the definition of Gaussian process. A Gaussian process, GP for short, is a collection of random variables such that any finite subset has a joint Gaussian distribution. So in essence, we are saying that if you put all the random variables together in a finite subset, it forms a normal distribution. That's what a Gaussian distribution simply is about. So it's about normal distribution. So we can then write that f of x follows the Gaussian process with m of x and k of x comma x prime. Of course, m of x is the mean. When we talk about distributions like that, the first thing is the mean. So m of x is the mean is the mean function, while k of x comma x prime is the covariance, or what you can call the kernel of the function. The intuition is that a Gaussian process defines a distribution over functions. And instead of predicting one function, it models many possible functions. Okay, so we talk about the mean and covariance functions uh, next. So first of all, the mean function m of x, as you saw up there, is actually some what we can call the expected value of the function f of x, and it is often assumed to be zero. It is often assumed that m of x is zero, whereas the covariance function k of x comma x prime is given as the expected value of f of x minus m of x multiplied by the difference between f of x prime minus m of x prime. That is the function evaluated at x prime minus the mean of the function at x prime. So the covariance determines the smoothness, the variability, and the correlation between points. So now we talk about the key properties of Gaussian processes. First of all, they are fully specified by mean and covariance, and then they are non-parametric, meaning that they are infinite. They have infinite dimensional. Gaussian processes are infinite dimensional model, and then they are Bayesian, means they provide uncertainty estimates, and then they are closed under conditioning. So those are some key properties of Gaussian processes. Then we talk about covariance functions now. So for the covariance functions, kernels, we saw the kernel k of x comma x prime, right? Define similarity between inputs, and a kernel must produce a valid covariance matrix, which is positive semi-definite. In case you're wondering what the positive semi-definite matrix is, you can check my matrix playlist. That was the very first playlist on my channel. So you want to check that out. Then we have the squared exponential, which you can also call the RBF kernel. So you have k of x comma x prime to be sigma squared exponential minus x prime squared all over 2l squared. And then the parameters as follows. L, for instance, is the length scale, which controls smoothness, and sigma squared is the variance. So, and it has properties like very smooth functions and and it is infinitely differentiable like that. So then we have other common kernels. So we can have them. Of course, the kernel we've talked about here is the squared exponential or RBF kernel. That's like the radial basis function kernel. So I believe that's what RBF means. So other common kernels would include things like the metan kernel, which is a k of x comma x prime, which is equal to sigma squared 2 raised by I minus nu over gamma of nu into square root of 2 nu multiplied by x minus the absolute value of x minus x prime all over L, all of that raised power nu, then you have k sub nu and all that. Then you can also have a periodic kernel like k of x comma x prime equals sigma squared exponent minus 2 sine squared into pi absolute value of x minus x prime divided by p, all of that over L squared. And then you can have a linear kernel like k of x prime, which is equal to x multiplied by x prime. Those are other types of kernels we can talk about, but the most common one is the squared exponential or the radial basis function kernel. Okay, and that's how we look at that. Now, talking about the RBF kernel, right? We can try to plot that, you know, you know, we have defined RBF kernel with x1, x2. X1, x2 would now be like the x and x prime, right? So, and you have one, the L equals 1.0 by default. If you don't specify L, so it should just be 1.0 sigma. If you don't specify sigma, so that's 1.0. And then you can return the expression sigma squared and all that. That's this particular expression for the kernel. And then you can do it over uh -5 to 5 on the x-axis, and then you have your k now. You have 100 by 100 thing going on there. So for I in range 100, then you do all of that, and then you plot that, right? So when you do the plotting, you get something like this. So um in that case now we have, no, this is 0 to, so you have the case, so like that. So you have a RBF kernel matrix this way. So you see the highest values are somewhere in the center here. And as you move away from the center, you go closer and closer to 0. Then we have the stationary correlation. So for stationary correlation, a kernel is stationary if k of x comma x prime is equal to k multiplied by x minus x prime. This means uh, the kernel depends only on distance. That's the distance between x and x prime, and it is not absolute. It does not. This means it is not absolute location. So examples include RBF, which is stationary, metan, which is stationary, and linear, which is not stationary. By the very definition of linear, right? It's a product of x and x prime. So it's not stationary. Then we talk about correlation function. So the correlation function, you have rho of x comma x prime equals k into of course, things like, of course, I have a statistics playlist which you can check out to see things like Pearson, Spearman correlation function and Pearson correlation and all of that. So rho of x comma x prime is k of x comma x prime all over square root of k into x comma x, k into x prime comma x prime. And interpretation is that for close points, you have high correlation, and for far points, you have low correlation. Okay, and then we can visualize that here. We define the correlation function, which is, this is minus x squared all over 2 times 1.5 times 2 now, you know. Then, we do that from 0 to 10, and then we plot x against the correlation like that. So then we have, this is the exponent of minus x squared all over this. I think this is the particular function we are looking at here. I suspect this, uh, oh yeah, I think it's this one, 2l squared or so. I guess it's this. So it's one of those functions. So you have the correlation here, and then you have, so when you plot that, this is what you get right here. Okay, so the correlation is high when the distance, so correlation of 1 when the distance is, when there's definitely no distance between the 2 points. So that means they are basically the same. So, but as the distance between the two values grow apart, the correlation tends towards 0. Then we can talk about Gaussian process regression. Gaussian process regression. If you are given training data x comma y, right? The way x is written, it tells you maybe you have a set of features. It's more like in data science where you have, say, I always like to use the example of the growth of a child depending on, say, nutrition, genetics, and environment. So x now, it encapsulates those three dependent variables, while y is the growth, which is the independent, x encapsulates the independent variables, that is genetics, nutrition, and of course environment, while y would be that growth that depends on all of those things. So we assume then that y, f star, is normally distributed with mean 0 and variance this is the variance right here. Okay, and then we have a posterior function where the mean is mu star to be k of x star comma x, k of x comma x all raised per minus 1 multiplied by y. And then the variance is sigma squared star equals k into x star comma x star minus k into x star comma x, k into x comma x inverse, then k of x comma x sub star like that. And then we can, do the plotting with a very beautiful plotting here. So we define the kernel x1 and x2. We take L and sigma to be 1 by default. Then, so here, flatten x1 and x2 to 1 day arrays before computing outer difference. So we have the square distance, which is NP to subtract outer x1 ravel, x2 ravel squared, then return sigma squared and all of that. And, by the time you go through all that, right, you get this beautiful thing down here. All right. Um, you get this right here. So you get the Gaussian process regression this way, like that. So, and then you can see the mean is going through the center like that. So that's the Gaussian process regression, uh, like we've seen there. Now we go on to talk about Gaussian processes for time series. So Gaussian processes can model trends, seasonality, and noise, and we can combine kernels. So where K can be like K of trend, kernel of the trend, kernel of the periodic, and kernel of the noise, right? Of course, trend is trend, seasonality is periodicity, and noise is noise. So we can combine Gaussian process, we can combine kernels for all of these things to form the overall kernel. So, and then that's the kind of thing we demonstrate in this next place here. So this is the Gaussian process time series modeling. So you have all of that. So you have this now. Then, um, so you have the Gaussian process time series modeling. So in summary now, we have that Gaussian processes model distributions over functions, and they are defined by mean and covariance, talking about kernel, and kernels encode structure, smoothness, and periodicity, and they provide uncertainty estimates, and they are useful for regression and time series. So we have limitations like computational cost. So the complexity is of degree 3, N3. So and the kernel selection is important when you talk about Gaussian processes like that. So we move on to the practice problem. So on to the practice problems. We have the first eight questions about conceptual questions. So this talks about defining a Gaussian process. How does it differ from a multivariate Gaussian distribution? Explore the role of the mean function and covariance. So we've talked about all of that. So you want to refresh your memory about all of this. So we then have some mathematical problems. Given the kernel k of x comma x prime equals exponent this, compute the covariance matrix K for imputes x equals 0, 1, 2. So um, you just fix these values and then you can compute the covariance. Then show that the RBF kernel is stationary by expressing it as a function of x minus x prime. Then given this, I'm going to solve this. I'm going to solve this on the worksheet. So given k is 1, 0 0.5, 0 0.5, and compute the correlation coefficient between the two variables. Then we have question 12, question 12, 13, 14 here. Derive the posterior mean formula mu star equals k into x star minus x, comma, I mean, multiplied by k x, comma, x, all inverse y from the Gaussian distribution. Given k of x, comma, x prime equals x prime, is this kernel stationary? Justify your answer. Of course, you need it's not stationary, so you want to justify that. Then next, we want to compute rho of x, comma, x prime equals k of x, comma, x prime all over square root of k of x, comma, x, k x prime, comma, x prime for the linear kernel. So, and then we have applied interpretation problems. So explain how Gaussian processes provide uncertainty estimates and predictions. Why do Gaussian processes perform well on small data sets? And what is the computational complexity of GP regression and why? Okay, we have saw that the complexity is O n3, that's order 3. So it's cubic. Then in time series modeling, how would you design a kernel to capture trend, seasonality, and noise? Of course, you put all the kernels together. You put the kernel for trend, seasonality, and noise together to form an overall kernel. Then coding and practical problems. You can write Python code to compute an RBF kernel matrix for a given data set. So I have a code already before. So you want to um, you know, use that and all that. So modify Gaussian processes regression code to include observation noise. So the code we had before, you don't want to add observation noise. So you want to explain the role of sigma sub n all squared like that. So like I said, I want to deal with question 11 so that this we can bring this to a close. So question 11 says, um, given covariance matrix, given covariance matrix K equals 1, 0.5, and 0.51. Okay, so we want to find the correlation coefficient. So we see that the correlation coefficient is rho of x1 comma x2, which is equal to k x comma 1 x comma 2 all over, I mean x1 x2 rather, all over square root of k x1 x1 k x2 x2. So that is what the covariance should look like. So if you substitute the values now, okay, but then before we even substitute values now, what is kx1 x2? Kx1 x2. So you may want to look at it this way, like this is K1, or you may want to look at it like this is X1, this is X2. So this is X1, this is X2. So X1, X2 will be 0.5. X2, X1 is also 0.5. So X1, X2 is the same. Then X1, X1 is 1. Then X2, X2 is also 1 here. Okay, so that's how to identify the values. So first of all, we should know that k of x1 comma x2 is equal to 0.5. So from this matrix now, x1, x2, that's 0.5. That's 0.5. And then we also need, from the formula, right? We need kx1, x1, and kx2, x2. So kx1 comma x1 is equal to x1, x1, that's x1, x1 here is 1, x2, x2 is also 1. So kx1, x1 is the same thing as kx2, x2, which is equal to 1, at least coming from the matrix. Then we can then go back to say that, so rho of x1 comma x2 now is equal to kx1, x2, that's 0.5, all over square root of kx1, x1, that is 1, multiplied by kx2, x2, which is another 1. So it means that this rho now is 0.5 all over square root of 1 times 1, 1. So rho is equal to 0.5 over 1. So finally, rho is equal to 0.5. So for that particular covariance matrix, so for K, which is 1, 0.5, 0.51, right? For covariance, if you like, for covariance matrix, that the correlation coefficient, the correlation coefficient is 0.5, like that. So you want to try your hands on the other questions. I'm going to just run through them. So again, don't forget to, try to get answers to this, and then these other ones. So I did 11 just now. So you want to think about the rest. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Okay. Um, if you have subscribed to this channel already, I thank you very much for that. But if you have not, you want to go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Okay, having done that, you can also become a member of the channel by clicking on join. That gives you some special privileges like getting to see some videos first before others see them, or seeing some videos exclusively because you're a member of the channel. Okay, you can also request for PDF copies of my notes, or we can hang out together physically if you're in the same geographical location at any point in time, or even online to discuss whatever interests you on my channel. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.